So H2O is building better predictions. It's focused on building a math engine in the open source and bring really state-of-the-art distributed better algorithms for big data and in a very classic, approachable way. If you love math and you want to change the world, we are also hiring. So if you're fun with math or systems hackers, you're looking for QA, white box testers, people who love numbers. And the impact of math is actually substantial. We're seeing traction across different verticals, even verticals we've not thought about. Our product is open source, free for cancer research. We want to solve the problem before it solves us, and stuff like that. So we're really a very young startup, a big data startup, well funded, but our focus is to leave a big intellectual legacy. That Hadoop is a massive opportunity, and there's not enough data scientists. So wasting data scientist time is like wasting real like trying to pure gold. The world never had enough mathematicians at any given time. It doesn't have enough of them today as well. And that's kind of why that's the focus of this era we're in, building tools so the day in the life of the data science gets better. And eventually we don't expect data analysts or business analysts to ever code. And so we want to make sure there's not a lot of map reduce being learned at the higher levels. We would rather have mathematicians get closer to business and solve real domain problems. At the highest level, what we do can be described in 3 pieces: exploration, modeling, and scoring. And exploration is mostly about ad hoc exploration. That's where the language piece comes in. Modeling is mostly about math, and so that's where our key focus for the company and the product has been. And real-time scoring is kind of the where velocity comes into play. So at the highest piece, we are building better exploration through R. So you can actually use your existing API like R and Python and JSON to drive our product. And we are working with messy data, try to help with missing elements and bring better data exploration at the upfront. We're munging, day-to-day munging, moving between tools, moving between different Unix consoles and MapReduce jobs. That's kind of where we want to actually give you a very easy experience, one single tool. And then further, we are focused on building very good high-scale regression algorithms, classification algorithms, and clustering algorithms. You're going to see random forest, which is one of the key classification algorithms we have that has taken a lot of our engineering. We have a very good implementation that will ask you to try and see how it solves your problems. Fundamentally, the real problem here is how do you solve unbalanced data sets? How do you actually make sure you can find the needle in the haystack when the haystack has gotten so big? Lastly, we actually are also building optimization for one of our customers, so that's also part of our roadmap. We want to give you the full end-to-end math modeling toolkit that you can take to any size data sets and any size machines. And scoring, which is actually kind of the low latency element of the space, where you want to take these models and put them in production and make them still go very fast, right? So that low latency is kind of the key part. So you can do hundreds of these models in a very quick fashion. So there's no one model for all of your data universe, and we want you to be able to use multiple models. And that's the only way to do that is your engine is really fast. And so that's kind of, we have a 100 nanosecond scoring engine that embeds into whatever system that your production systems are. And so you can actually take that to production. So you build your models, your offline scoring gets as good as your online scoring. So you have more confidence taking your modeling to the market. So we have a fantastic team that puts all these 3 together, very different pieces. One of them dealing with language, other dealing with data and math, and then low latency. All this without forcing a net new API. We don't want the world to learn. There's enough languages already, and it's going to be a polyglot world, so let's embrace it. We will take your languages and then make them scale. So in some sense, we have a future for a fast R project that Jan's also heading, that now takes our input and scales it on bytecode that we have as Java. The other big piece that has been of concern is more data better or better algorithms better, and different camps in the valley as well and across in New York. One of the things that we want to stomp is you don't have to make a choice. You get more data and better algorithms. Right? So you take the best, latest algorithms. So we are actually one of the future roadmap pieces. We have GBM that we're taking, trying to scale it on big data. Other pieces, we have people who are fanatic about Boltzmann machines and stuff like that. So we are trying to take these new latest algorithms and apply them at scale. So it's not just more data or better algorithms, go get them both and solve the problems. And still, so the real key piece is not necessarily algorithms, it's the next step. How do you discover insights in your data? Finally, we're not yet another big data startup trying to make money. We are trying to leave an intellectual legacy. We really believe that math needs to be free. And it's tens of thousands of years of evolutionary knowledge. And that needs to be a platform that anybody can access and build, get better tools and applications on top of the core math platform. And that's why we are actually a very open source company, and we want to build a great community as well as community of users, developers, extenders, build applications. We want to support you guys to go use the math. One of the fundamental discovery, one of the shocking discovery that we had as a company was there's not enough math being used in the businesses, in the enterprises in the world. And that's something we're out to change. We're trying to evangelize and going to all these meetups, talking directly to end users is one of the core philosophies we have picked up. And we are trying to evangelize the use of better math and use of better technologies for solving your day-to-day problems. And so that's, GitHub is open. We are going to make it's Apache V2 license. We expect people to eventually go and become part of Apache Software Foundation. But we want to make sure we get to high velocity before we get into the committees. It's a fantastic team. We are hiring, but our team of very solid systems engineers, but also very good data science advisors. Stephen Boyd, Trevor Hasty, and Rob Tipshrani, and we're going to the source. So whoever has invented the technology, the algorithm, you're going to them straight and asking them what are the better ways to do it. How do I take your Fortran implementation so it scales better? How do we take that and apply it for a very highly unbalanced data set? And that's kind of the real heart of the problem is how do we take this great algorithms in R and implementations in R and make them widely accessible to a great audience. And that's kind of one of the core pieces behind it.
So random forest is an algorithm that was devised originally by Leo Breiman and Adele Cutler a few years back. It synthesizes a number of ideas that were floating in the community. And we'll start by introducing a few of the key concepts so you can understand the rest of the talk. And I'll try to be as self-contained as possible. So, starting with the beginnings, we'll start by describing what is a classification tree. So imagine you have a very simple data set. It's composed of red and green dots, and they are living on a plane, 2D surface, with coordinates in x ranging from 1 to 4, and y from 5 to 8. Okay? Simple enough. And imagine that the goal we set ourselves is, given a new observation, pick a color. It's going to be red or green. Simple, right? And if you look at the board, some patterns may emerge. It's not completely random. So how are we going to decide what our color to assign to our new observation? Well, one way to do this is to build a classification tree. So, for instance, here's one that I'll build for you. And basically, this tree says things like this. If your x-axis is, so let's start at the root, is larger than 3, and your y-axis is larger than 6, that's this corner, you're going to get red. And basically what the tree does is it describes this chessboard in fine granularity so that every point point is identified by some leaf node in the tree, and all the leaf nodes have a single color, and therefore now if I come with a new observation, I can just figure out in which node it will fall and say, ah, you know, it's red. Okay, easy enough. So another way to visualize the tree is to think of the tree as painting the surface with these colors. And wherever you land in the 2D space, this is the color you will get. Okay? Now, the obvious thing is, the first thing that comes to mind when you think about it a little bit is that, you know, this is just one small sample of the population, and you know, this painting here doesn't quite match our intuition. If you go back one thing, you know, our intuition, if you look at this from a distance, is roughly that these squares are red, these squares are green, roughly said. But if you look at the painting, you know, you have this whole band here that shows up as green. So what we're doing is we're overfitting the little data we had to generate, you know, this classifier. All right. So the idea of random forest is really simple. It's, you know, you start with the original population, and to avoid overfitting, you're going to build many trees, but many partial trees, many trees that are kind of wrong. But the idea is, you know, if you put lots of people who are kind of wrong together, you get American democracy, or you get a random forest algorithm. So let's see. So how do we do this? Well, we take our original population, and then we're going to sample it, get subsets of that original population, and for each of those subsets, so these are two subsets, they're overlapping, right? They can have the same observations. And for each of those subsets, we're going to build ourselves a tree using exactly the same approach as before. So here's a tree for one subset, and here's a tree for another subset. And the interesting thing about those trees is there will be points where they disagree. You know, this point here, I'm saying that things that are in that corner, let's see, larger than 3, larger than 2, larger than 6. So I forget what I was doing. But there will be points which disagree. Why? Because you have different, you know, different populations. And yes, this square, for instance, in this tree has only a green dot, so it's a safe assumption that you'll classify this space as green, whereas this square happens to have only red dots, so it's a safe assumption that you'll classify this as red. But the thing is that by randomizing and seeing only some small part of the population, we're going to create a combined classifier that it performs better. So the parts where the three agree, we're really sure about. The parts where they disagree, it's up for grabs. Okay, so there are a couple more things to introduce about a random forest. So this concept of taking random samples is called bagging. Basically, the idea is each tree will be built on a different subset of the population that you take without replacement from the original. And that's a very simple thing. And then the second concept is how do I grow my trees? Well, I'll grow my trees by, at each node, selecting the split, this value of one of the feature that best separates my population. And you have different criteria, such as Gini or information gain, which you can pick from to do this. And then you keep on growing the trees until either you hit a limit or you get leaf nodes that are uniform in one population. Then once you have a set of trees, the way you use them is for each new observation, you will simply vote. You will say, I have this new point, I'll classify it with which trees, and I'll pick, you know, if 60% say red, I'll say red. Simple enough. So there's a couple more small things to talk about. One is the notion of error. So Breiman had this very elegant way to evaluate the quality of a forest. This is what he called out-of-bag error. And basically the idea is as follows. Each time we build a tree, so we pick a sample of the population and we're going to use that sample to build a tree. What we're going to do is remember all the observations we did not use to build that tree and use those observations to evaluate that particular tree. So you have 100 trees, they're built with 100 samples, and they're evaluated with 100 complements of those samples. So for instance, if I build a tree with this sample, and I evaluate it with this one, I'll get most likely errors around here, because here I only saw green and the complement has red, and here because I only saw red and there was a green dot. Okay? So out-of-bag error is this error estimate that you can use without any special data. You can use it, you can create an estimate using the same data you use to train and build your model. And lastly, how do we know how well we're doing? Well, at the end of the day, you will have a validation set, say, and you will build yourself a confusion matrix of this kind, which says, well, you know, I've predicted that 15 observations were red, but you know, there were and 5 greens, and this is your assigned versus actual, and this gives you a notion of, you know, this in this one I have 33% of errors on this class, and here I have 10% error. All right. Any questions? That's a quick whirlwind 7-minute tour of what random forest is about. Okay, so what we could do is just show you how it runs. Yes?
How do you combine the trees?
How do we combine the trees? So we have a bunch of trees, and we just classify observation with each tree, and then you vote. And then you can set the voting criteria to what percentage you want. So for instance, in some cases you may be interested if the typical thing would be 50%, but you may be interested in cases where there's even a small chance that, you know, something is of a particular class. So you can set the threshold. Make sense? Right.
So how do you deal with the missing variable?
Aha! So the question is how to deal with missing observations. Well, there's two things that we worry about missing observation: when we build the trees, and then when we classify. And so, a couple of options. You could throw away the rows, but that's in practice really bad because a lot of data sets have a lot of missing observations. But if you have a data set that has many features, it may turn out that you actually never visit the missing observation. So what you could do is say, well, you know, if I actually try to use a missing observation, I'll throw away the row. Another thing you could do is, if I try to use a missing observation while I traverse a tree, just randomly pick left or right. You could be more clever and say, well, I'll use the distribution of values in that column. You know, there's a number of things. In our current implementation, we just randomly pick. Okay? Yeah?
Sorry if I missed this. Do you also randomly sample while you're building the tree? They're built on random subsets of the available features?
Yes, I didn't mention that, but yes, that is another part. So each time we look at a split, we're only evaluating a subset of the features. And I'll come back to that in a later slide, because it has, how many you pick actually has an impact on quality of your results.
essentially this is so using the same kind of command that we saw earlier. Simple one jar file. One of the things I asked the team to build is to make it very easy to deploy. I bootstrapped the company teaching Hadoop, so I don't want anybody to teach H2O or how to install it. It should be that simple to install. So it's a very simple, easy to install product that clusters, give it 1.5 users. What we're seeing, and if you want on the main page, is a simple tutorial, which includes random forest tutorial. So if you, there's a data, so this connects you to the wiki page, so you can actually learn more about it. So there is a data ingest piece where you can import from a URL or HDFS. In this particular case, we'll import from HDFS. HDFS backed by S3. You can actually look at some data sets here. Call type is the world's most popular, or our most popular data set for doing random forest. Can I give a general separator here? Get a quick summary of your data. Get a quick summary of the data. Min, max, missing, mu, sigma, kind of. This data set is doing forest coverage type. So trying to predict on response rate of 54.
So set 10 or 20 trees. We'll see the impact of the number of trees later.
So one of the things you try to do is to optimize the number of trees in traditional R implementations.
So Cov type has about 500,000 rows, roughly. 500,000. Yeah. And here, we're building the trees incrementally. Yeah, sorry. We're building the trees incrementally, and as we build the tree, we're building the OOB estimate. So what we're seeing here is the OOB estimate with only part of the trees built, and the page will refresh as we get more trees. The classification error, so this is the aggregate classification error, which stands at 30%, and that's pretty bad, typically decreases.
In this particular case, it's so fast. It's on 16 machines, so it's finished very fast. So we can rerun with more.
Right, and so if you add trees, you will get a better results. And that's sort of the general principle of random forest, right? Is that putting more of those weak classifiers together gives you better prediction abilities. So, now we're running it for 100. And, oh, it's done? Oh. So usually on my laptop it takes a minute or two. I have time to talk through it.
Let's get more bigger data.
Bigger data? All right.
Can I ask a quick question?
Yeah, sure.
So what are the chances of increasing overfitting by generating many, many more trees?
So generating many, many more trees would not necessarily increase overfitting because each one is built on a distinct subset. So none of them sees the whole data, so they're all sort of wrong.
Okay.
Now what happens is, after a while, adding trees doesn't help anymore. So, and depending on your data set, you'll see the curve of how many trees or what's the contribution of each tree changes.
Do you guys have visualizations so that you can see convergence?
Not right now. So this is the current. So we have two APIs. One which is the web API, and the other one is an R console that we're in the process of building. And I think we will put some more smarts in the console once we have it.
One simple question.
Yeah.
So for each member-reduced job, right, are you building one layer of the tree or just build a single tree?
Wait for a little bit. I'll tell you all that.
Okay.
Hold that thought. Yeah.
Did you show the confusion matrix recovery type? What was the overall accuracy on
So,
classes?
so he switched. Yeah. So typically, the one we had for 10.3 was 30%, which is quite awful. And you can get all the way to 4% with more trees and tweaking things a bit, and I'll mention that.
You should be able to get better than 90% accuracy with...
Well, 4% is the number of errors.
Oh, I see. So
switch it.
96% accuracy.
Yes.
Oh, good.
Yeah. So which one are we doing now?
I'm just rerunning while it's parsing the big data.
Okay, so we're doing several things at the same time. So what is the big data?
Yeah. So the big data is all here.
Right. So the big data is the airlines data. That's 12 gig. It's not a big data set, but it's bigger than the others. We're doing two things at once: building 103 COP type and parsing the airline data set. And it is probably going to take a little bit because the airline data set usually takes a little bit. We have to bring it from this. We have to read it a couple of times and parse it. Did it finish?
For the system gigs, we made sure there's enough stuff in there so people can actually monitor, manage, cluster. But fundamentally, the goal is that the end math person is trying to look at the HTML bottle, macro, HTML stack. Kind of take that.
Right. So, but I think we've got the point. Let's go back to the top. So. Yeah, so typically you get confusions matrix like these, and if the trees are small, we can either print them graphically. It's a cute feature, but in practice it's never used because the trees are big. Or we can generate Java or C code that encodes the tree that you can use to run this as for classification and scoring. All right. So I said we looked at some other tools. There's a number of implementation of RF. Ours is distributed, but we couldn't get any license for another distributed system. So here what we're doing is comparing the accuracy of different tools on the single node status. And there's a set of, there's a few data sets. They go from here, you've got the stats, but roughly said, these are tiny and these are small. So small means 100,000 to 500,000 rows. Tiny means, I don't care, it's just very small. So we compared our implementation, the standard R implementation that Breiman did, Weka and WiseRF. And for each of them, I show the error rate. So lower is better. We want fewer errors. And the bold numbers are the best for that particular data set. And well, what can we say? Sometimes we've got the best results. Sometimes we're not too far. Interestingly, for COF type, we get 3.6% error, whereas R gets 22%. And that's a really big difference. I don't know why. It may be that R cuts the size of the trees. That's my best guess. There was a question.
Are these all using the same C function for any randomness that you're doing?
No. So the problem is sometimes we can, sometimes we can't, and the random number generators are different. So yeah,
Are the number of trees the same?
Yes. So all the other, all the knobs we can play with are the same, and we try to get for all the tools the best possible results playing with different knobs to the best. All I'm claiming is in 2,000 or 3,000 lines of code, you get a competitive tool, right? If you want to spend more time, you can do probably better. All right, so the interesting part, for me as a computer scientist is, well, how do we build this thing? How do we build this algorithm? especially since it's for a distributed and parallel setting. So a couple of questions. So if your data set doesn't fit in one computer and you want to parallelize things, there's a couple of questions you have to answer. One of them is, well, I said we're going to sample the data for each tree. So imagine I have 12 gigabytes. How do I create for 1,000 trees or 500 trees, 500 different samples of 12 gigabytes? How do I select the splits, the point at which we separate the population? How do I estimate the out-of-bag error? Again, if I have to do this on a very large set of data observations and for many, many trees. So we had a couple of insights, nothing terribly surprising. The first one is, if your data fits in memory, then parallelizing this algorithm is really, really simple, right? Because all of this is very independent, so you can run you can build your tree in parallel. You can have one thread per per leaf that you're building, and it works very nicely. Different trees can be built in parallel. Again, trivially, each tree is independent, so you can build them in parallel. Now, an interesting observation, which we didn't think of at first, is that the tree size grows a lot. So, essentially, the trees are describing all the nooks and crannies of your data. The more complex the data, the more sort of nodes and branches. So trivial data sets, small trees. Large data sets that encode a complex function. Remember, the RF only can say, oh, it's larger or smaller. So you're describing a function by a sequence, oh, it's larger, and that's a very coarse way to describe complex functions. So if you have complex data and lots of data, your trees tend to become very large. And lastly, if I want to validate a tree, compute my out-of-bag error, I have to have the tree together with the data on the same computer. That's obvious. Well, that means now I have to make sure trees are available on a cluster. All right. All of these are things that are worth thinking about when you design an algorithm like this. So the strategy we picked is the following. We decided to say, well, what we'll do is we'll do a first step of randomization where we randomize the data over the cluster, and each node has a view of a subset of the data, and it works with that. So if we're building a tree, we're going to build it node local on the subset of the data that is on that node. And then, we can build trees on parallel on all the nodes, and we can build trees also in parallel within a node. And then, when we want to do validation, we're going to flood the network with trees. And these can be, easily 100,000 of split nodes, so fairly large. Okay. So what I'll do now is I'll just step through some of the interesting parts of the algorithm and tell you how to do this. So, the first thing to note is we're not starting from scratch. We're building on top of the H2O infrastructure. And what H2O is good for is that it's a good engine for doing distributed computations. So it has two things. It has an abstraction of key-value pairs where keys are unique strings and values are vectors that can span many, many nodes. So first abstraction. The other abstraction that it has is it has a distributed fork-join framework. So in Java, there is a notion of fork-join framework for concurrency, and we've added distribution to it. So we can distribute tasks over the cluster and parallelize them within a node. So the question of map reduce is addressed by a distributed framework. So distributed fork join means I'm forking threads, and the threads are migrated silently to different nodes, and they run on those nodes, and then they fork subthreads that are running on that node. Okay? So one way to think about the H2O system in the long run is to think about it as an operating system for doing distributed mathematical computations. Okay? It has a store, it has threads, it has resource management, it has all of this. So for the first bit, how do I read and parse the data? Well, for me it was easy. I just defer that to the infrastructure. The infrastructure has a notion of value array, which is like an R data frame. And a value array has rows and columns, and it has a function to read a particular observation in the value array. The value array is chunked at 4 megabytes chunks, and the chunks are randomized over the network. So when I read a big file, 12 gigabyte file, that file is sprayed through the cluster in 4 megabyte units. So, parsing is done, no code to write. Extracting random subsets. So for extracting random subsets, the strategy we picked was to say, well, what we'll do is we will have a local cache of data, and that local cache of data will be built out of all of the chunks of the input array that are node local. So this is done in less than a page here in H2O. So we say, this is my data key, this is the name of the file I've parsed. I read it from the key value store, I get a value array. I create an array of jobs, and then for every 4 megabyte chunk that belongs to the value array, if it is located on the current node, I create a job, and what the job is that it will read all the data in that value array and put it in my local cache. And then I invoke all my jobs. This runs in parallel and slurps in all the node local data in a representation that I find useful. Okay.
One question, the cache is in memory or in HDL
So
system?
the caches are in memory. And if the memory starts to, memory pressure starts to increase, H2O will start to evict some of the chunks to disk. So silently, there is the Java garbage collector and the H2O memory manager, and the H2O memory manager talks to the Java garbage collector, and when it sees that memory is running low, it starts to push stuff out, and if that's not enough, we die. Okay? So the next interesting bit of the algorithm is how to split the data. And roughly, the way it's described in the Breiman algorithm is, I have this sequence of values. So the way it works is, remember, I'm building this decision tree. At each point in the tree, at each node, I have some part of the population, and I want to split it in left and right. So imagine that this is the subset I have at one particular node in the tree that I'm building. What is the best split? So the way Breiman describes it is, first you sort the values by the feature you're looking at. So this is sorting them in order of increasing value. And then you find the best point where to split. Here it's pretty obvious you want to split here, and you get a very nice red-green split. But that means sorting at every node in the tree. And every node sees a different subset of the original sample it had, so there's not much you can do. And you can have all over 100,000 nodes for a big data set. That's a lot of sorting. So what we do is we turn the data, we discretize the data. So for every value in the original input, we turn it into consecutive numbers, 1, 2, 3, 4. And furthermore, if we want some compaction, we will bin a number of consecutive value in the same number. And then what we do is, then we don't have to sort, because we can just use an array and store all those values, think of those values as indices in an array. And the split function, which I will not detail, is this, not more than that. And it's basically one big loop over all the values, all the distinct values in your feature, and then a number of loops over the data, and you're done. No sorting, nothing. Just normal Java, easy to write.
One simple question.
Yeah.
So is it possible to run into, I mean, because when you deal with the big data,
Yeah.
Probably you have lots of, I mean, distinct variables, such that it's gonna run
Then
out.
you can bin. You can aggregate a number of values into the same discrete number at the cost of some precision. And you know the choice is, well, do I want a precision and speed and decrease speed, or yeah.
Do you guys try MDL?
Sorry?
Something like MDL, MDL, I mean, or something like yeah, minimal discretion, yes, something like that.
We didn't try anything more than this.
Oh,
This
yeah.
is as far as we got. Remember, not a data scientist, 2,000 lines of code. It's a small budget and small brain. So, and the last bit that I want to mention is how do we parallelize the tree building? And there it's a simple case of fork join. And this is lots boring code, but essentially what you're doing is for each node, you're creating a left and right, and you are going to fork a thread for the left and a thread for the right. Now the fork join framework may not fork, it will choose whether it actually forks or not. But as far as programmers go, you consider that you forked and you forget about it. And that's probably all I have to say about the implementation. So while building this, we found a number of fun observations. One of them that Java is a very, very pleasant language to work with. It has lots of libraries. The libraries are very good. There is a random number generated class, and that random number isn't very random. Okay? And it showed up in surprising ways. We were getting bad error rates, right? So it actually, the quality of our result was like twice as worse as R. And this was just because our random number generator was returning sequences that were not that random. So we implemented our own random number generator, then we realized that the Sun random number generator is okay as long as the seed is really big. So that's a good thing to know. Yeah.
How big?
Basically, it has to be a long, and you use enough of the bits. It's open source. You can look. It's documented exactly how much we had to add. Tree size gets to be a challenge. Big trees are hundreds of kilobytes, hundreds of megabytes. At some point, it's not 100 megabytes, up to a megabyte. If you have lots of them, it becomes a problem. I said that we randomize by spreading 4 megabyte chunks and using all the chunks that are on the node. But that means our randomization is only at 4 megabytes boundaries, which is not great. And that's an engineering thing which we should just fix. Randomize much better. And then last thing that's as a message for anybody building things like that. Build the algorithm so it is deterministic. Yes, it's a random algorithm, but make it sure that you have a mode where you can repeat and get exactly the same result. So it's already hard enough. The thing with statistics, you always get a number. 42. Good number or a bad number? It's 42. I don't know. You ask the domain people, they'll tell you, oh, 42 is a great number, and I can give you an explanation why. You come a week later and say, actually it was 24. Oh no, yeah, I can give you an explanation why. Yes. So, really hard. Testing is important. So last tiny bit of this talk is we played a little bit with the knobs of the algorithm. And this is just telling you which knobs are interesting and worth looking at. So we have these data sets. This is about cough type, which is describing forests. As I said, we have 500,000 rows, and typically we use 300,000 for model building and 200,000 for validation. So the first thing we did was we varied the sampling rate. So this is from 0 to 100, and the sampling rate is how much of the observation do I use to build each tree, right? And it's a valid question. How much should I use, right? Could use 1%, and then I get errors that are really high, or I could use 100%. And for cough type, it seems that the more I use, the more the blue line is the validation error, the better I get results. But it's not the case for all data sets. And the red line here is the out-of-bag error, and it's sort of interesting that as you have more and more of your data that is used to build each tree, the out-of-bag error becomes meaningless. And why? Well, because it has so few observations that it becomes very chaotic. But for the rest of the curve, they follow each other fairly nicely. So the out-of-bag error is a good predictor of your actual error. So the other thing we played for was, so somebody asked about this number of feature per split. So the algorithm, each time it evaluates a split, doesn't look at the whole set of features, but only a subset. And how many of them you pick matters. So here, what we're showing is blue is our classification error, and we show, this is the error rate, this is the number of features you use. So cough type has 50 features, so we can use from 1 feature all the way to 50, and the different lines are for different sampling rates. But let's take the bottom one. The bottom one is for an 80% sampling rate. So you see that as I increase the number of features, my error decreases, and then around 30 or so, which is about half, I get the best result, and then it becomes worse. And what this sort of suggests is, again, overfitting, right? You see too much of the data, I'm overfitting. Another fun thing to do with cough type is you can drop out certain features completely. And you see that, for instance, so these are the feature numbers, and this is the impact of dropping one of them. So if I drop feature 0, my error goes to 8%. So worse error, that feature is really useful. But if I drop out feature 1, my error goes back to 4.5%. So feature 1 is actually confusing your algorithm, right? So the more data doesn't mean the better results. All right, so coming to the end. So what did we see? We saw random forest, cool, powerful machine learning algorithm. My claim is it's actually easy to write a distributed and parallel implementation if you have the right tools, right? It's not that hard. It took a couple of months to get it right, but if I had to do it again, it'd be a couple of weeks. Different implementation choices are definitely possible. So the way we're building things, we're doing this siloing of the data per node, that is just a choice. And whether it performs better or not than some other implementation, that remains to be evaluated. And for us, I think we want to scale to terabyte data, to see whether, because it's very likely that when you scale up, the current approach won't work. It's just too much data, the trees will be too big, so what do we do? And I don't know, we need to actually see real data to be able to tell. That's pretty much all I had to say for today. Thank you for your attention. Any questions?
So where is the model being stored and how is that managed?
Right. So the models, the trees are stored as key value pairs in the cloud key value store, and you can any node can request them by providing the key for that model.
And then when you provide that, you mean
For each tree.
for each tree, but what if then I guess there's a
And there's an aggregate for the whole forest. Yes.
So, if you're a fan of programming languages, why didn't you use Scala instead of Java? It would be 200 lines instead of 2,000.
And it'll be 2 times slower, but who cares about performance? No, Scala, Scala is a wonderful language. Spent 6 months with Martin Odersky about 7 years ago, previous sabbatical. It is a language that dangerously pushes the limit of human understandability in its type system. I work with R. R has no types. I find that, useful and handy. And so I don't know. It's just familiarity. There was a question here.
How many more lines of code to do RF-based regression instead of classification?
Right. So regression we haven't implemented, and our belief is not that hard. But this is, the usual thing in computer science. Yeah, that feature, no problem. 2 years later, oh well. Yeah.
So I guess my question is kind of in 2 parts. Can you give us a sense, given how much data is on a single node, how much memory footprint is being used, like what the ratio is? And number 2, given the size of a data set, how much computing resources do I need to train with your implementation of a random forest?
Yeah. So the 2 questions were how much memory, if I have, let me rephrase that, if I have 1 gigabyte of memory per node, how much heap do I need to provision for the Java VM? So that roughly
or how much, what is the limit in the size of the data that can be processed on a single?
Well, the limit is clearly how many gigabytes of RAM you have. And we typically require about, say, twice 2.5 as much heap as the data. Okay, so we're running on 500 gigabyte heaps. But that tends to be expensive. The other question was the speed at which,
given a data set, let's say it's 100 gigs. How many
nodes?
How many nodes do I need? What does the configuration have to look like?
So usually we have run, so it depends on what you have, right? So we have run with 16 cores, 10 gig nodes, and for 100 gigs it'll be probably in the 20s or so. Depends, because we compress the data as we parse it. So the 100 gigs may end up being much smaller if we're lucky. And the other thing is the complexity of the data is going to drive a lot of the speed and space cost. So imagine that all of your observations are completely different. There's no redundancy. Then your tree will be the size of have as many leaves as rows. Not good, right? But the hope is that we're looking for patterns and that we can collapse things. And this is the interesting question: how far can we? And what we've seen is up to now that the bigger the data set, the bigger the trees, and the bigger the trees, the more accurate. So whenever we cut down on tree size by imposing a limit, we lose on accuracy. And that becomes a very hard problem, right? Because you really like that accuracy, but it costs. And that's a trade-off that depends on what your end goals are and your data set is. Yeah. So the depth or just the number of nodes. You could have a very deep single line tree, which would be fine. It's the number of leaves that matters for.
Are you guys building any additional functionality for
pre-process the data to cut down the branching factor?
Whether we're building facilities to cut down the branching factor. So one of the things we're doing is by binning some of the values, we're sort of decreasing the number of distinct observables, and that will decrease your branching factor at the cost of precision. And that's the only thing we've come up with so far. There's one question back.
Yeah, I want to ask about your observation that the larger the data set, the more the trees, the larger the trees.
Yeah.
My understanding is that one of the trade-offs that you're allowed to do is you can have weaker classifiers, so smaller trees,
Yeah.
but just have a lot more of them.
Well, so yeah, I can speak to that a little bit. So the question is, well, wouldn't it be just better to say have small trees but millions?
Yeah.
And the problem with that is often, since it depends on your data set, but imagine that your data set has many features. The likelihood at the top of the tree, none of those features will select very well. So you will pick random features and they'll cut the population in half randomly without really increasing the information content in each of the partition. And it's only when you start to go down to smaller sets that you start picking up information. So my intuition is that artificially cutting down the depth of the tree really hurts you, especially for large data sets. And I don't have a good answer because it sucks. Larger trees are really expensive. Yeah.
Those accuracy numbers that you showed, was that Gini or InfoGain? And do you have any
So InfoGain, Gini didn't, InfoGain was better than Gini pretty much in all our data sets. Not by much, but yeah. Since I had implemented InfoGain, I kept that one and threw out the other.
Did you do any variable importance? Can you display variable?
So we haven't implemented that. It's easily done. Blows the 2,000 line budget, I think.
Okay.
So what would happen if one of the nodes failed during training?
Good question. So H2O is an operating system that is not yet fault tolerant. So currently, if you lose a node, it's just like you lose a little bit of your RAM. Bad things happen. We have plans to make things more fault tolerant, but it's unclear that the extra costs are worth it. So a lot of our computations are done in matters of minutes, and the feeling is, if we can keep, down to minutes, then just rerun the thing with fewer nodes. If we get to the point where you're running 24/7 with one cloud that stays up, that's a different proposition. And different engineering choices will have to be made.
Do you try to do the regression type? Regression type tree, regression type.
No, we don't do that yet.
Okay.
He doesn't mean regression, but cart instead of.
Oh, cart.
Yeah.
Oh, sorry. No, we haven't implemented it.
Part of the large roadmap that.
It's as Sri says, it's part of our roadmap. My sabbatical is ending. That'll be his problem.
I was going to point to the airline that you said, which we finished short for us, but continue with the Q&A.
Yeah. Any other questions?
As you can tell, Jan picked up random forest. Thank you, Jan. So yeah, 2.5 years ago, I remember distinctly on University Avenue running into Jan, was presenting at Stanford, and said, Jan, I can't run the random forest in R, it's just too damn slow. And well, sure enough, he kept his word and came and joined me on a sabbatical and built a fantastic random forest. This is all 20 years of data set. I remember, all airline 20 years data set, and I think this probably finished in like a split second. We didn't rerun it, but random forest is, it taught us a lot. So if anything, it was the first algo we built, and it took 2 months, it extracted its cost, but the core platform has gotten so much better.
While he's running this, I'll say, if you want to build something like this platform, what is the hardest problem ever? The hardest problem is parsing the data. If you can, so in Java, the joke was, if you can run hello world, you have implemented Java. Here, if you can parse distributed, uncompressed, from S3, do on the fly in-memory compression, you're good. Everything else is easy.
It's no different from your day-to-day life where munging is like the 98% or 80% of data science. So this, I mean, we have a very good, robust roadmap, actually. GBM is coming up. We have a very good GLM, thanks to Rob and Trevor. Put up the roadmap here. But this roadmap is a function of the number of users who have asked us things. So this is not a static PowerPoint. We actually took input from customers, end users, and community. And no product is complete without the community, and especially in the open source, we want you guys to chime in on what you need. If GBM is your next big problem, we're going to pick that up, or if it's working machines, that's going to come out. But we pick what we have is on the leftmost corner, we actually have random forest, ADMM, which is the latest technique from Stanford that gives us ways to do. There's a fantastic talk tomorrow on some of that stuff, and next week and the week after. But we really are looking to the community to chime in on what they really want to do with the platform. It's a first step. We have some big algos, but we want to make sure it actually does solve some real world problems. Here's the 20-year airline data set predicting airlines like with more than 98%. Thinking maybe there's a couple of more columns to ignore, which will make them even better. But random forest definitely goes after some really, the more data you have, the better it gets. So in that sense, big data and random forest are actually a match made in heaven. And so if the system can scale, you guys have a fantastic, powerful tool to go back to, not just to Kaggle, but to take back to your own implementations into your own day-to-day and make a fantastic impact. But so one more case in point I want to bring up. This is not the end of the random forest, it's the beginning. It's kind of useful, but we need the people talk about variable importance that comes up, so that's right there on our roadmap. People want regressions, card trees, and that's a fantastic request. So there's roadmap pieces. People who are capable can contribute or just chime on issues or things that you want, and you want to make sure, even if Jan's going back on sabbatical, some of the students are really building some of the core gut VMs of Safari and other fantastic things that you're using. So he's a prolific producer of great engineers. So thanks, Jan, and thank you for coming. If you have any further questions, feel free to email us.